Wow, there's a lot of people. Where are you guys watching this from? So let's wait maybe 1 more minute for everybody to connect. And then we're going to start with a special session today. I'm here today with the tech giants. So the tech giants are a group of super smart people from ALX cohort 9 and 10, right, guys? And today they're going to show how to create your own malloc. So if you've been here before, you know probably what malloc is. You've done a little bit of C, and you know that malloc is used to dynamically provide memory that you have to take care of after that. You're going to be responsible for this memory. So it's a very important piece of software when you build software with C. And you know, those tech giants, you know, like try to think about how they could build this malloc themselves, and they're going to explain to you how they did just that. They're going to start with a naive one, and then, you know, the version above, and maybe like in another session the version above again, until maybe we get to something that is even better than the malloc that you are working on. So with that said, I'm going to give Daniel the mic to introduce the session.
Thank you, Mr. Julian. Good afternoon, good evening, good morning, wherever you are. This is Tech Giants, and my name is Dale Daniel, and I'm live in Uganda. Today, we are going to be talking about malloc, as Mr. Julian has said. And he has made a simple introduction of what malloc does. Normally, its main use is just to help you allocate memory dynamically. And this memory, you have to cater for it afterwards. Allow me share my screen, walk you through the agenda of what we are going to do. Then from there, you can see how we are going to be moving.
Daniel, you're on mute since you moved to the presentation. Daniel, you're on mute. Can you hear me?
Yes, I can.
Okay.
Let me try and share again. Sorry, guys, about that. Okay.
It's not working.
Why? I guess I'm having a technical problem with my machine. I don't know.
No problem. Can you send me the presentation? And then I can present while you speak.
Yes, I can. I can share it now. Mr. Julian, check the chat section. posted. Okay, as Mr. Julian is working on that, I don't know what's wrong with my machine at the moment, but as I was saying earlier on, we are a group of 8 people, and most of us, we are in cohort 9 and a few are in cohort 10. We went ahead and got an idea from Mr. Julian, and we were asking ourselves what normally happens whenever whenever you allocate memory, whenever you call malloc. So we went ahead and looked underneath what happens, and we are happy to come and share with you guys. Maybe you can also go ahead and look or find out with us what really happens, because we use functions, we use libraries, but most of them we don't even have an idea what they do, or you may even use it and not even go into depth with it. Guys, keep the chat flowing, keep connecting. My name is Dan, and I'm live from Kampala, Uganda. Then allow me introduce our sister to Luwani. She's a student. She's in Nigeria, and she's going to take us through the journey of Malloc. But before I hand her the microphone, kindly, if you didn't watch our first part, kindly go revisit that. It's under this YouTube channel. You can watch it and get more depth of what we are talking about. Maybe yeah. Luwani, you're welcome. You're welcome.
Thank you, Danny. Hi, everybody. Welcome to the live coding session with Tech Titans. I'm Toluwani. I'm from cohort 9. And in this session, we'll be recreating 2 versions of the malloc function. We'll be recreating a naive malloc and an optimized version of malloc. Before I go into explaining the technical terms, I would like to describe the malloc function now.
Toluwani, you're on mute. I think I'm going to have to be the one presenting, and then you can talk over. Just tell me when I need to go to the next slide, okay? Sorry, everybody, for the technical issues. Now that we know what's wrong, it should be fine and smooth. Okay, Toluwani, you can go ahead. Just tell me when I need to go to the next slide, okay?
Yes. So I would like to describe the malloc function with the story of a businessman. Next slide, please. Malloc is a businessman who recently decided to go into drop shipping. How this works is Malloc would order products from a supplier, and when a customer requests for that product, he would deliver it back to the customer. Malloc currently doesn't have enough money to order these products himself, so he has to wait for a customer to order a product before he can get it from the supplier's warehouse and deliver it to the customer. So Malloc was kind of the middle supplier's warehouse and deliver it back to the customer. So this is the naive Malloc. This is how we'll be implementing the naive Malloc. So what happens is, in this case, Malloc is our businessman. The heap is the memory being requested for. C is the supplier. The heap is the supplier's warehouse, and the user is the one requesting for memory. So in more technical terms, the malloc function is a function that allows C to allocate memory dynamically from the heap using program breaks. So when a user asks for a product, when a user asks for memory, a system call will be made and memory will be allocated. Next slide, please. Next slide, please. Yes, I'll go ahead to explain some terms in memory. So this is currently what the memory looks like. The text segment is where executable instructions are stored. Next slide, please. The data segment is where static and global variables are stored. Static variables are variables whose lifetime is the entire runtime of the program, while global variables are variables that can be accessed globally. That is, every function can access them. Next slide, please. The stack segment is where variables declared inside functions are stored. Next slide, please. The segment above the stack is where environment variables and command line arguments are stored. Next slide, please. The program break PB marks the end of the heap. So we can see where it is there, where the arrow is pointing to. If there's no heap, the program break marks the end of the data segment. Next slide, please. The stack goes downward and the heap goes upward. As more memory is being allocated. Next slide.
Okay, guys, so a little bit of network connection. Stoliwani, we can't really hear you. Just like real life happening. I'm just gonna go over this slide and then go back to you, Toliwani, just to make sure that everybody have heard the most important part of what you were saying. So essentially, here on the left, you have the virtual memory, and Toliwani just explained to you like the most important segments that you're gonna find in this virtual memory and where they sit. at the end of the data segment is where you have your program break, that you can call PB, right? And then every time you're gonna work with the heap, it's gonna start right here at PB. So you're gonna extend the PB every time you malloc something. Every time you do memory allocation, the PB is gonna extend, is gonna actually extend the data section. Okay, next slide. Toliwani, back to you. Let's try to see if we can hear you. Okay, so still a little bit of network issue. Everybody knows what it is, so be mindful. All right, so as we can see, the heap extends starting from the data section. This is, you know, the illustration of what the two of us were trying to say. Toliwani, it seems that you are back. I can see your video. Do you want to try to talk? All right. So the way we manipulate the heap with malloc, actually malloc uses this system call called SBRK. This is the syscall that is used to manipulate the program break and extend the heap. So the first version of malloc that we're going to do is by playing with SBRK only. So no free associated with that, but only the my malloc with, it's going to take a size as an argument, just like the regular function malloc. And the size is the number of bytes you will want to allocate. So when the function is called, you can see like the start, we're going to have the size. If the size is less than 1, then we're going to return null. It means that you don't have anything to allocate. And then this is the end of the flow. If the size is at least 1, then we're going to store the program break in a variable start that we're going to call start. And then we're going to increase the program break by calling SBRK with size. And then we're going to return start to the calling function. This way, it's going to have the function that had called my malloc will have the address that they can use to store whatever they wanted to store, just like when you call malloc. Toliwani, do you want to take over? Okay, still some technical issues. Why don't we go into the code of what we just saw? Dave, do you want to take over?
Okay, so I just want to quickly go over that slide, the last slide that was shown before.
Yeah.
All right, now, so the next one, there's the next slide after it.
The next is one?
Okay, yeah, exactly. So if you look at this slide, guys, if you look at this slide very well, you see we have a virtual memory. Like this is a representation of the virtual memory. Now look at it. We have a call to my malloc on it. Like on top, you'd see a call to my malloc, and we're passing 98 to it. This means that we're trying to allocate 98 bytes. Do you get? So we're trying to allocate 98 bytes. So let's see what happens behind the scenes in the memory, in the virtual memory, when we actually call my malloc. So, sir, just please help me with the next slide. All right, you can see what actually happened. So we have starts. Now start represents the start of the new memory we just allocated, right? That's the part that you can now put whatever you want to store inside. So start is the address of the new memory we just created, and PB is actually the program break. So you can see the program break shifted up right? So that's the entire heap that we have there. The entire heap is now 98 bytes. So sir, please next slide. Let's see something happen. So you can see this is another representation of the virtual memory, right? This shows you when we've already allocated 98 bytes, right? So now we're trying to allocate other memory. Let's see how the virtual memory reacts to it again. So sir, please just help me with the next. All right, so you can see we actually allocated 1024 bytes. We allocated 1024 bytes, and you can now see the start. The start has shifted from the beginning of that 98 bytes to the beginning of the 1024 bytes. Do you see? And you can see the program break way up there. Do you see? So the program break shifts as we allocate memory. That's what we're trying to show. And I actually go into the details. I'll code everything for you so you actually see how it works, right? So that's a great idea. So, sir, please, next slide. I think it's about time I just.
Okay.
All right, so now let's watch as Dave. I'm actually Dave. So let's just watch as I walk you through the this version. So we have a very simple version. Just stay with me. Let me share my screen ASAP. All right, can my screen be seen? Is my screen visible? All right, so I'll just show you something real quick.
Is it possible to widen it a little bit, Dave? Because right now it's
I'll try to widen it, sir. So if I do ls, we have one file, special.txt. I'll work on widening my terminal. So there's something special inside there. Let's just look at it. We have special.txt. So you can see it's actually just but it's special because just pay attention to what's about to happen in this. Don't leave, don't go anywhere. So let me clear my screen and I'll widen it. All right, so is this better, sir?
Perfect.
All right, so let's go. So you can see there's actually nothing here apart from this file. So we are going to be creating everything from scratch. So first thing we want to do is we want to create a header file. So you know what a header file is? A header file is just a kind of file where you put function prototypes, right? You put function prototypes, you put what do they call these stuff? Macros, yeah, macros. So probably once you start doing C, you will learn about header files, macros, and everything. But let's quickly create it fast. So I'll do malloc.h, right? So we have malloc.h. And what am I going to do there? I'm just going to write one simple stuff. You don't need to understand it. If and def malloc h. Let me write this in caps. H, yeah. Define. Oh, sorry about that. That's in caps. Define malloc h. Then I can do end if. All right, so in between this, I'm going to write our function prototype. So this is our function prototype, pay attention to it. So this function is going to return a void pointer. Now, what is a void pointer? A void pointer is a kind of pointer that can be casted into any type. So let's say you were trying to store a number inside the allocated memory, right? So definitely what you need is an integer pointer. It could be a float, it could be an integer. Those are the kind of numbers you have. Or if you want to store a string, that's text, right? You need a character pointer. That's a character pointer, that's what we call it. Or if you wanted an array, we have different kind of pointers though. But the void pointer is like, what do I call it? Like an anonymous pointer, anonymous. So it can be casted into different pointers you get. So that's why we are returning a void pointer. So we're returning a void pointer. The name of the function, as you've seen, is my malloc, right? And it's going to be taking a size t. Size t is just a fancy word for a long integer. That's just what we call it in C, right? So it's just a fancy word. It doesn't really mean anything. So size t, right? Then because we're using size t, I have to include a library. You might know of it. So this is standard def.h. All right, so let's go. We have this, and next thing we want to do is actually look at the man page. So I'm going to do man to SBRK. I'll come back to what I'm doing to man to. Why did I not just do man SBRK? I'll come back to that later, but let's just look at it. So now if you look at it, you'd see some stuff. So you see SBRK and BRK. This one, BRK, we have SBRK. I'm not going to be talking about BRK for now, but let's just look at SBRK. So this is change data segment size. Do you get? Now you need to include this library. They told us to include this. So take note, this is the first thing we're going to do. We're going to include this stuff, right? The next thing, you can see what this stuff is doing. This one is also returning a void pointer. You get, the name is SBRK, and there's this fancy word here, which might just mean an integer. I think it's just an integer. Yeah, it's just an integer. So you pass how many sizes you want to increase, and it increases it for you. So let's look at the description. BRK and SBRK change the location of the program break. This is exactly what we want to do. We want to change the location of the program break. We want to shift it upward. Do you get? So, okay, location of the program break, which defines the end of the process's data segment. So the program break is the first location after the end of the uninitialized data segment. Okay, what this is basically saying is with BRK and SBRK, you can actually change the size of the, you can increase, you can decrease. What we want actually now is to increase, we are not decreasing. You get? So if you come down here, you can actually see that SBRK increments the program's data space by increment bytes. What they mean is that you have to pass, like, if you pass 35, it increases the program, it shifts the program break by 35 bytes. Do you get? That's what they mean by increment bytes. So calling SBRK with an increment of 0, that means if you pass 0 to SBRK, you can use it to find the current location of the program break. So we might need this later, so just take note of this. Calling SBRK with 0, we can use it to get the program break. So you can just jot that down somewhere. So if you wanted to get, if I ask you next time, how do we get the program break? Just tell me by calling SBRK with 0. So now we know that SBRK returns a void pointer, which is actually what our function would return. So it's not as if we're doing anything with it. So let's just start, right? So we have malloc.h. Now we are going to create malloc.c, right? Or should I call this my malloc? Let's see. No, let's call this malloc.c. We'll create another one. Maybe we'll call that one my malloc. So let's go. So first thing we want to do is include what? Include malloc.h. And also remember that other thing I told you about that we're going to include. So we'll include uni_std.h, right? This was it. So now our function, we have a void pointer called my malloc, right? Then it's collecting a size t called size, right? Now let's see what we're going to do. Now, if you remember from the flow chart we saw, first thing we did was check if we created a variable which is start. So it will be a void pointer that's going to store. We'll just do start is equals to, we need the program break. So how do we get the program break? Do you remember how do we get the program break? How do we actually get the program break? Okay, that's very correct. By using SBRK 0, SBRK 0, we get the program break, right? Now, the next thing we want to do is we'll check if, remember, if size, remember what the diagram you saw, if size is less than 1, that means if they cannot allocate 0 bytes, it's not possible. So that means they're playing with our function. We just return null. You get? Return null. Null means nothing in C. Like we're not returning anything. It's just empty. You get? So if size is less than 1, we return null. Now, if not, so should we do an else? Okay, let's do an else. Else, what do? We'll call SBRK with size. right? Now it has shifted the program break, but the initial program break, we have it stored. So what are we going to do? We are going to return it. Return start, yes. Right? So let's check this out in action. So very simple, you can see it. You can take a screenshot of it so that now you know how to create your own malloc. So let's go, just you could take a screenshot of it. And now we're going to create our main.c file. Main.c is for testing. We just want to test it out to see if it actually works, right? So in this main.c file, I'm going to do include what? Malloc.h, right? So if I include malloc.h, then I'm going to do int main, right? I'll just have to put void there. Don't ask me why. You learn why you put void later. So it's not really important you know why you put void there. Just focus on the function I'm about to write. So we have int main void, right? So first thing we want to do, we want to create an integer pointer. We want to store an integer inside the memory we allocate, right? So we'll create an integer pointer called int pointer. Okay, we'll also create a float. Is there some? Yeah, there's float pointer called FLT pointer, or let me just call it float pointer. Float pointer. You get? So now, next thing I want to do is I want to create a string. A string is basically a character pointer. So a character pointer is a string. So I can just do character pointer and I'll call it string. You get? All right, now it's time to allocate memory. So first thing we need to do is we need to call my malloc, right? So we'll do int pointer is equals to what? My malloc. What is the size of an integer? We don't know. I don't know. Do you know? So we can just do size of. Do you get? Size of int. Yeah, it makes sense. So that's it. Now we'll have to check if it is null. Remember that our function could return null, have you? So we have to do if int pointer is null. What do we do? Let's see. So I want us to print something. For us to be able to print something, we need to include a library called stdio.h, right? So we'll know if something actually happened. So if int pointer is actually null, we have to printf, right? You come across printf very soon. So we have printf could not allocate. Then we have a new line at the end, a fancy new line, and we return. What do we return? Return 1 to show that an error occurred, right? If no error occurred, that means 0. If an error occurred, we can use 1, we can use 2. But if no error occurred, we can use a 0. Do you get? So that's it. Now, if int pointer is equals to null, print could not allocate memory, right? Now let's do the same thing for float. But to save time, I'll just quickly copy it. You get? So let's just quickly copy. If you're using VI, we have how many lines that we're trying to copy? 1, 2, 3, 4, 5, 6. We have 6 lines that we're trying to copy. If you're using VI, you can just do Y6, 6, then you do $sign. If you look down on my screen, you see something like 6 lines yanked. So you can come down to this line, and you cannot do P, right? So you just have to do small fixing, and yeah, we are there. So I'll just change this one to float pointer. Right? So you can see just copy and paste. I did then size of float, then if float pointer. Okay, that's just it. And I can do the same thing for string, right? Then I can do P again. Now I'll come and fix it up. If string is equals to malloc size of what now this time? Okay, it now depends on how many characters we want inside that string. So I can do size of char, times, let's say we want 6 characters inside there. 6. I think 6 is fine. Or let's do 20. We might not use everything. But let's do 6 so that we just put a small string inside. So we do 6 if string is equals to null. Right? Are you with me? Stay with me. If string is equals to null, then we print could not allocate memory, return 1. Right? Now the next thing to do is actually now put values inside. So we do int pointer is equals to what? Sorry, you have to dereference this. How do you dereference? I think it's at the ending part. I can't really remember. So we have int pointer is equals to what? You now put a value inside. Let's put 1024. I've started to like that number because of ALX. ALX uses 1024 back to back every time. So I've fallen in love with that number. So we have float. So we have float pointer is equals to, let me put another number that ALX uses every time. So we have 98.7, right? Now, the string, how do we put stuff inside the string? Now, the case of the string is kind of, I don't know, I think it's different. So we can do something like this. We can do like the string 0 is equals to h, right? So we're trying to put LO inside. We have string 1 is equals to E, right? Stay with me. String 2 is equals to L, right? String 3 is equals to another L. Then string 4 wait, calm down.
Hello, Dave, you muted.
Okay, can I still be heard? Okay, I guess I can still be heard. So the last one would now be string 5 is equals to what? We have the null byte. That's the end of the string. Every string ends with the null byte. So we have this. Now we're trying to print this out. So we print f. So first thing we're going to print int pointer is what? So we use, what do we use? We are trying to print the value inside int pointer. So we use an integer I, right? I think we use an I, then we put a new line after it. Then I'll pass the value of the int pointer.
Dave, your screen is frozen.
My screen is frozen. So sorry about that. Let me fix it up. Okay, can my screen be seen now? Can my screen be seen now? Okay,
No.
not yet. Let me see.
So while Dave is coming back with his screen, I see a lot of people from cohort 12 in the chat, and you guys are like a little bit lost. So this is normal, don't worry. This was a session meant for C11 and before. You're all welcome to stay or to leave. This is not mandatory, so do as you wish. I think it's really cool as cohort 12, like in your first week, to stay to see what you're going to become. Because those guys has been like in the program for a few months, and in a few months, you're going to be in a position to understand everything they say and maybe like do a live session too. And doing a live session is really hard because you have the stress of having like 1,000 people watching like every character you put on the terminal, and also like every word you're saying. So please be nice with everybody. Again, this is not mandatory. Please stay if you want to understand who you're going to become in a few months. Otherwise, you're free to go. Back to you, Dave.
All right, so thank you very much, Sam. Let me share my screen. So can I be seen now? Am I back? Am I back on?
We can't see your screen.
Not yet.
Your video is
Not
frozen.
yet. What's going on?
Okay, try to maybe disconnect and reconnect. And while you're doing this, I'm going to take some questions. Or maybe you guys are going to be able to answer. I think the first question is, does the system recycles until the number less than 1 is reached at the end? And then end. And I think this goes back to, you know, Toliwani, the explanation you made in the chart flow, in the flow chart. Do you want to try to show us again and see if you're back online?
Yes.
Toliwani, we can't hear you. Let's wait a second. Okay. We lost the screen and we can't hear you. Okay, so in the flow chart that we showed you earlier, we said that if the size is less than 1, then we return null.
Try that now.
Toliwani, are you back? Yeah, I think it doesn't work. I'm gonna mute you. So the answer to the question is like it's something different. So we do this, it ends because the user is asking for a space in memory that is 0 or negative. You can't allocate a negative amount of space. It doesn't work in the real world, right? It works in mathematics, you know, negative numbers, but in the real world, you know, it doesn't really exist in space in memory. Yeah, so if this is the case, we just return null to say, hey, we have not allocated anything for you, which is, you know, what we actually ask for. The second question was like, can we allocate our malloc memory in our main.c instead of a different file? Yes, you can do this, but you're going to see that this is the naive function, the naive version of the malloc. And then you're going to have like something much more complicated. And it takes a lot of time, a lot of lines, so a lot of space. So you don't want to create this function or like to put all this code every time you want to allocate something. You really want to separate like those big functions into different files and then call them. So that's the idea behind.
Mr. Gillian, maybe to add to throw more light about that.
Yeah.
For our brothers, why we do that is in case of debugging. Once you put code together, debugging it becomes a bit difficult. But once they are separated, when you're trying to compile it, if one of your files has got an issue, so the compiler will tell you where it is exactly. So it becomes easier, and you save a lot of time compared to when you put code together. Thank you.
All right. Are we covering casting too? So we don't. So in C, when you return a void star, so like a pointer to anything, you don't need to explicitly cast this into the variable type. So you don't need to do that. You can do this if you want to, but you don't need to. Does it only work on VI? I don't know what it is. I don't know VI. I think Emacs better. So I don't want to talk about VI. I think this is outdated. Any industry use of this? What? Everybody in C uses malloc. So I don't know where you get this idea from. Can we allocate malloc in our main C instead of a separate file? Yes. But as I said, it's better to separate like the function into a function so that you can call it whenever you want. And then like once you have written this, you can call it from any other program. Just like take the file and use the function. You don't want to have to rewrite everything again and again and again. And then the final one before Dave comes back. What should happen for this malloc function if the problem hits the stack? If the PB hits the stack? It's a great question. If the PB hits the stack, the breakpoint, it means that the data section has reached so far that it's going to go touching the stack. And then you have like no more memory. In reality, it never goes that way because it never goes that far because actually there's something in between. But let's imagine there's nothing. In theory, once the heap goes into the stack, the OS is going to say, hey, like this is over. You can't allocate more memory. So there are some securities by the OS to tell the process, hey, stop what you're doing. This is too much space. All right, Dave, back to the code.
Yes, sir.
Let's go.
All right, can my screen be, okay, wait, let's calm down. Can my screen be seen now?
Yes, that works, and we can see it. We can see it properly. Yes, great. Thank you.
Okay, awesome. So, great questions, actually, great questions. So, let's just quickly rush through this because we have an even more interesting version of malloc coming through. So let's just rush this one. So we are just going to print. Okay, sorry, my print F. Now I'm going to print the float pointer, and this one is going to be, I think it's a %F. Can't remember. So then we have the float pointer, right? The next one we're going to print is the string. So I'm going to print the string. Then we'll do this one is going to be a %S. Then we'll do a new line. Then at the end, instead of passing %string, I mean, instead of putting the asterisk before the string, we just put string because that's how C likes it. So at the end, we'll return what? A 0 because what? Because nothing happened. That's in there was no error. That's what I mean. So let's quickly test this out. Now I'm going to do GCC. I'm going to compile malloc.c with main.c, right? Hopefully we don't get any errors. Okay, there's one error. We have, okay. So that was actually an oversight. So I think it's this part. There's an asterisk before the 9, which does not make sense to the compiler. So we should be good to go like this. Okay, we have int pointer is equals to, okay. There was a name error there. That was also an oversight. So instead of int pointer, we have int prt. So it's supposed to be int pointer and it should be fine. All right, we're fine. So ./a.out compile, we run it. So we have int pointer is equals to 1024, float pointer added some extra digits at the back, but it works. Now the string actually works because we have hello. So you can see this is actually quite amazing. And at this point, I'm going to pass on to Lu so that she continues, so that I come back to the more interesting version of malloc. So just stay put. Just grab your seat, grab your popcorn. We're coming back to this. All right, so.
Okay, thanks, Dave. This was like really cool. And I like the fact that you stayed very calm when you saw all those warnings and errors. And then you just like read the error message and, went directly back to the code. I think this is a great example on how, a software engineer thinks. Like most of the time when you write a lot of lines, it's not going to compile right away. You're going to have to do like typos and mistakes. But like the important thing is that, okay, like there's an error. I stay calm, I read the error message, and in this case, this was enough to solve the issue. So great job. Toluwani, are you back with us? Can you use your mic? Toluwani, you're still on mute? Can you say hello, hello, hello to see if we can hear you? Ah, yes. Are you here?
Can you hear me? Please?
Yes, we can hear you very well. So let me project the rest of the presentation while we have you, and hop, and you tell me when I need to move the slide. Okay, let's go.
Okay, I can't see your screen yet.
Can you see the screen now?
Yes.
Okay.
And we're back. So
Yes.
remember the story of Malloc that I was telling earlier, so my network went off. So I said Malloc went into the business of drop shipping, and when a customer places an order, Malloc would take the order to the supplier and deliver it back to the customer. That was the naive Malloc that Dave just coded. So now Malloc's business has started booming, and he now has a lot more customers than before. So what Malloc decided to do was he invested in a warehouse and he started ordering products in excess. So for example, if a customer should order 3 packs of bottled water, Malloc could order 30 packs of bottled water and keep the rest in his warehouse. So in case another customer wants to order a pack of bottled water, Malloc would simply go to his warehouse and deliver the product to the customer. This is the optimized version. So with this method, Malloc was able to reduce the number of trips he had to make back and forth with his customer. Next slide, please. Yes, I said we call the Malloc function with a system call. SBRK is a system call. Next slide, please.
When we can't hear you anymore. Dave, can you mute yourself, please? Toliwani, can you hear us? Are you still with us?
Yes, I can hear you.
Okay, good.
Can you hear me?
Can you try to turn your video off to see if we can have a better network quality? Yeah. Okay, go ahead. We can hear you.
So like I said earlier, Malloc used this method to reduce his number of trips which he was making to his supplier. So this in turn reduced his cost of production. Now we call the Malloc function with system calls, but system calls are hard work for your computer's CPU and they slow down the runtime of your computer. So we decided to come up with an optimized version, which would not make as many system calls as the naive version would. Next slide, please. Yes, I said repeated use of system calls tend to slow down your computer. So we came up with an optimized version of Malloc, which wouldn't make as many system calls as the naive Malloc would. Next slide, please. This is the flow chart for our optimized Malloc. So first we'll start the process, then we'll accept input from the user, which is size. We'll initialize static variables and set total to 0. We'll set used to 0 and set start to the initial program break. Then total is the total number of bytes we have. Used is the amount of memory that has been used. Then we'll declare new variables, ALX size and new mem. ALX size is the total number of bytes that we want to have, while new mem is the used memory. So if used plus size is greater than total, and used plus size is greater than total plus ALX size, we'll increase ALX size by 10,000 bytes. Then we'll call SBRK with ALX size and increase total by ALX size. But if used plus size is not greater than total, we would simply increase total by ALX size. Next slide, please.
Toluwani, you're still there?
Yes, so we'll continue the process. And if size is less than 1, we'll return null and end the process. But if size is not less than 1, we'll set new memory to the value of start. We'll increase start by size, increase use by size, and return new memory, then end the process. Next slide, please. So let's see what happens behind the scenes when we allocate memory now with the optimized version. Next slide, please. Yes, so I'll go ahead to show us what happens behind the scenes when we allocate memory now. Next slide, please. Yes, so this is the memory. And when we call the malloc function with 1024 bytes, that means we want this system to allocate 1024 bytes. It allocates the 1024 bytes, but we can see that 10,000 bytes were already created. So let's go back to the story. I said when a customer orders for 3 packs of bottled water, Malloc would order for 30 packs. This is exactly what is going on here. So 1024 bytes were allocated, but a system call was already made and 10,000 bytes were created. So the user has used the 1024 bytes. Let's see what happens next. Next slide, please. That is where the memory is starting. That is the 1024 bytes is what the user wants to use. Then the whole of this is the unused parts. Then we can see where our program break is starting from. Next slide, please. The user called for 2048 bytes again. The user wants to use 2048 bytes. 2048 bytes were allocated, but a system call was already made, which allocated 10,000 bytes. So now the user can use the 2048 bytes, but there's still excess memory on the heap. Next slide, please. So now total used is 3072 bytes. That is the start of the memory allocated, and this is where the unused memory is. Always the program break remained. Next slide, please. Now I'll be handing it over to my teammate Dave, and let's watch as he walks us through the implementation of the optimized version in C.
Thanks, Toluwani. Super clear explanation. Dave, you taking over? Dave, you're on mute.
Okay, sir, can I be heard? Can I be heard? Can I be heard? Can I be seen? Okay, sir, please, can I be heard?
We can hear you.
Yes, Dave. Yes, Dave. We can hear you.
You can, okay. So let me just share my screen again. So I will start. All right, so let me clear up my screen and we'll actually do something great. Look, can I still be heard? I don't know. My network started messing up.
So right now we can hear you. We can see your screen. And the
Okay,
screen
so
is
let
just
me.
my malloc with the prompt.
Okay, so now we'll be working on the optimized version of Malloc. Yeah, we're working on the optimized version of Malloc, right? Now, let's look at it. So this one, we're going to call it my Malloc. So I'll just vi my malloc.c. We still have our header file, which we have the definition, the prototype of my malloc. So we're going to include it. Include what? Include malloc.h, right? Yeah, sure. So we have include malloc.h, and we also want to include what? Include standard. No, we need standard. No. Wait, yes. Sorry about that. .h. I actually forgot what to include. So we are going to be returning a void pointer this time, and we're going to call this one my malloc, right? Same thing. So we have a size t, but now we're going to do something different. Now, based on the story Tolu just told us, we are going to actually be writing a malloc based on that story. You get it? So that the story can really resonate, you can actually get what the story is telling you. So this one, I'll be calling this size t, I'll be calling it what? I'll be calling it orders, right? So we have the orders that the company, the customer placed. We have the orders that the customer placed, and we have a static variable, which is called, what should we call this? Goods. Let's call this goods available. Static good at variable is going to be an integer, right? Available. Yes. So we have the goods available, right? Then now we also have a static what? A static total. Let's call this a size t.
Dave, we can't hear you anymore.
That flowchart again, because I've gotten confused at this point. So we have size t total. Sir, please, can I quickly look at the flowchart again? I know this is where it gets confusing. Thank you, sir. Slides.
Okay, while we're waiting for Dave,
let's
Dave, Dave, take your time. I'm gonna answer like a few questions, okay?
Okay,
And you just
sir.
tell me when you're ready to come back. Are you ready to come back?
Okay, sir.
Okay. You just stop me when you're ready to come back, okay? Does VI have a console? How do I know syntax error? So VI is a text editor, just like Emacs. I encourage you to actually use Emacs instead of VI, because it's much better. But it doesn't really have a console. So the console is what you see like in black. This is the Linux terminal. So you quit VI, and then you go back to the terminal, you go back to the prompt, the shell prompt, and then when you compile, you're going to see the syntax errors, if you have syntax errors. How can I solve overflow in heap? So you're not going to have to do this. The OS is going to tell you this is not possible, and it's going to either give you an error or stop the program entirely. What happens to the excess memory left over after the user uses part of it? So the excess memory, you remember what Toliwani was explaining to you. So you are the customer, you're asking for 1,000 bottles of orange juice, and then you go to the wholesaler, which is the OS, and you say, okay, with HBRK, you say like, give me 10,000. So those 10,000 are sitting in the virtual memory. And then you tell the function that called you, hey, you can use those 1,000 ones. But in store, in your warehouse, you still have like 9,000. So it's still here, it's sitting in memory, it's not used. But the idea is that whenever you're going to come back to me and ask me for another 1,000 of bottle of orange juice, I'm going to give you like a tranche of those 9,000. I'm going to give you another 1,000. And then you can call me 10 times. And even when you call me 10 times, I only use one syscall, one call to the SBRK, one travel to my supplier. So I need like a little bit more space. There's a little bit of waste, but it's not a lot of waste, especially compared to the speed at which you're going to be able to give those orange juice back to you. Because then you don't have to do the SBR call, and so you can like give it away right away. So you have the visitor coming to your warehouse. Hey, like the bottles are here. You take this into your truck and then you go. Otherwise, you come to me and then I have to go to the wholesaler, to my supplier, and you negotiate with the supplier. Hey, like this is my turn. Like give me some memory, and then I come back, with those memory orange juice, and then I can give it to you. So the speed is like much faster. So that's the trade-off. And 10K in memory lost per process, it's not a lot on most of the machines. When you're going to go into like embedded, very small, like IoT devices, for instance, with like only like a small amount of memory, you will never do something like this because you don't have extra 10K sitting, there. But in most of the cases, when you have a Linux machine, you have like plenty of memory. So it's fine if you have like 10,000 bytes, left over. And especially with the speed at which your program is going to run thanks to that. This way of doing things is actually how the real malloc works under the hood. It never calls SBRK all the time. It calls SBRK or BRK once, like he has like a lot of it, and then he's going to give it to you slice by slice until he has to reorder to the OS with RBRK or BRK again. So this is actually how the real malloc works. Dave, are you good? Or should I continue? Okay, let's continue. Please, can we get the code when they're done? No, you can't. The idea is you want to listen and you want to watch, and you want to understand everything that we are explaining to you, so that then you can like start and learn. Again, this is not mandatory. This is for you to understand a little bit deeper compared to what we are used to. We do like a lot of things at ALX already, so don't worry if you don't have time to do this additional work, but like try to understand how everything works, the process, by which we are going through things. And why I'm saying this, one of the important things that you have witnessed here is you haven't seen Dave or anyone rush into the code right away. The first thing is that Toluwani explained in very simple terms how everything is going to work, how the virtual memory work, like what's the context? This is the virtual memory, what are the different segments, where is my heap starting, and how can I manipulate it? Then she went into a flowchart. Okay, this is how everything is going to work. I'm going to name my variables those ways. If, size is less than 1, I'm going to do this. If it's more than 1, I'm going to do that. Once we have the flowchart and we know exactly what we want to do, then Dave took over and started coding in C. So translating this flowchart into a programming language. And this is very important to separate like those steps, especially when you're a beginner. And everybody here is a beginner, no matter like C12, C10, C11, C9, everybody's a beginner. So make sure that you focus on one problem before you go into the next, because doing everything at the same time is not going to work. It's going to be like 1,000 times harder if you try to do all those 3 steps at the same time. So try to make sure you understand the context, you understand, like the goal of the function that you're going to do, understand how you can things, understand like all the tools that you have at your disposal. In this case, SBRK mainly, right? And then you go into the flowchart. Okay, this is how this is going to go. And then you go into the code only when you know exactly what you're going to code. You don't go to the code, you don't go to the terminal, you don't open any editor, VI nor Emacs, unless you know exactly what you want to write. This is like super, super important. If you do this, everything's going to be like much easier than if you try to do everything at the same time. Dave, are you back?
Yes, I'm back.
Okay, want to take over?
Yes.
All right, let's go.
Okay, so. Okay. While while I was away, I was actually writing some stuff. So look at it now. So we have orders that are coming in, right? So size T is just a fancy name. Let me be on camera so you see my face. So size T is actually just a fancy name for a very large number. You get. So we have orders coming in, right? Then we also have the total goods. The total goods we have. Then we have another one, the sold out. Out of the total we have, the ones we've sold out. Do you get? The ones we've sold out. Do you get? Now watch this. So we have total goods available, the ones we've sold out, right? Now we also have new normal variables. So we have a size T needed. So this is the total number of goods that are needed, and then we have a void pointer, which is going to call. We are going to call this is going to be our supply, right? So this is going to be our supply. This is what we're going to supply to the customer. So let's go, guys. So based on what based on what was explained, they said if what we used that's sold out, that's what we've sold out plus what is needed, that's the orders plus orders, is greater than what the total number of goods we've ever ordered. Do you get that? Total goods, I'll call this total goods, right? If what we have used plus what we want to use is greater than what we have, do you get it? What do? We enter a while loop. We say, we now do this. We say, while what? While okay, supply is going to be 0. Let's do needed is going to be 0. So needed is 0 for now, right? So while sold out plus orders is greater than total goods plus needed, the ones we need, right? So please just hang on. I have someone at the door. So sorry. This is really bad. So sorry. All right,
Okay,
so
no problem.
I'll
Are
just
you
need to
back?
continue. I'm back as back. So what we have used, what we want to have. What do? We increase what we want to have. We do what we want to have. What we want to have that's needed is plus is equals to we add 10,000 to it. So that's 1,000. We have 10,000 to it, right? So at the end of this, we'll now increase total at the end of this. So it will eventually break out of here, right? So where's my cursor? All right, good. Good is we add what we want. To it. So we now have SBRK. Okay, supply actually looking. I'm actually looking at the diagram here, so I can flow. So then we'll check if others so I'm writing Python. If others is one as usual, right? So we don't want any negative. And okay, something I did not do something yet, so we'll do if start. Take note, if start, since it's start if we want to do start SBI is the rate. Then you see how this actually applies. Then we return all, we set new memory, that supply is equals to start, right? Now increase start by size. So start would not be equal to the program hierarchy. No. This is equals to start load. So we have then want to return increase used. What we use is sold out. So increase sold out. We sold it out now since we already packaged everything. So we can just add it to what we sold out. So we do sold out plus equals, right? Just return we can return supply. You get return the supply back to the customer. And this might seem long and kind of, but let's just test it out first. Let's just test that if it actually works. So we'll test it out by doing GCC as we did before, but instead of calling malloc this time, it will be my malloc. Remember, thankfully no errors. We'll now do a out, and you see, boom, it actually worked. But this might work exactly like the last one, but this is actually every time. So now I'm going to test by reading a file out of text, right? So I'm going to clear my screen and actually read a file. So definitely today you're going to learn how to read a file in C, right? Then we'll read it at least. Let's see what's inside our film. Get ready, grab your popcorns, and let's do this. So to read a file, I'm going to call this one vi file.c, right? Then I'm going to include FC what? FC NT see slash start. I'm going to include slash pipes each. This one. So we have include, right? Then last but not the least, I'm going to include starts. We have starts, we have types, we have FC10 type starts. So I think we're good. We're good to go. But lastly, let me include for the printing out, I include standard IO.h. So this is how we're going to do it. We have our int main function. This is the main function. Come across so many times.
Dave, you're breaking a lot. I'm going to give you like a few minutes
first thing
to solve your issue.
do trucks.
Dave?
No, this is it. So my network is breaking. So I can hear you.
Okay. Let me take a few questions while you're trying to solve this, okay?
Okay.
Okay, so a few other questions. What is the largest memory that can be malloced? So actually it depends on your system. It depends on like a lot of different things, the OS, and also the RAM that you have. Because at the end of the day, you know, like those segments that you allocate are somewhere in the RAM, which is like 90% true. It's not exactly true, but like, you know, for today, just think as, you know, everything is mapped in the RAM. But actually like it's going to use the disk and other stuff on top of it. But like at the end of the day, like the idea is that if you have a big machine, you're going to be able to allocate more memory than if you have like a very small machine. Okay. I think I done all the questions. Didn't I? So we need C plugin to be able to code with it. In order to code with C, you're going to need basically a text file and a compiler. That's just it. No plugin, it's just like a program. The compiler is a program that is going to read through your C file, the file you have written, you are written with an IDE in the language C, and then transform that into an executable that you're going to be able to run on the same system it has been compiled on. In the char data type, can we allocate the size of char in a variable declaration or only when calling the malloc function? So if you know exactly what how much space you're going to need for your string, you can right away, you know, pre-allocate, but with like an automatic allocation of memory. You can do that by declaring an array of chars with the size you want. Remember to add the \0 at the end. Why we're doing this today is just to illustrate the malloc function. What is Dave's doing right now is that he's taking actually like a real life example of a program that's going to take inputs from the user. And before you run the program, you have no idea how big the input is going to be, right? So if you take a file and you open a file, you have no idea beforehand how big the file is going to be. So Dave is now going to read this file, which has like a lot of text, and then allocate, you know, the size needed in memory to fit that file. Okay. What else do we have? Want the simple mymalloc return an error because of assignment of an int to a void star without a cast. So in the code that Dave showed, there was no casting from a pointer into an int. Otherwise, the compiler would have given at least a warning. So what you saw is a pointer to a void, which means pointer to any type, casted into a pointer to an int. So it was an int star, not just an int. Otherwise, it would not have worked. Okay, Dave, do you think you're ready?
Yes, I am.
Okay, let's go.
All right, so we have a start buff, right? Don't worry about the start buff for now. Then we also have a size. This is the size of the file. That's the number of characters inside the file. Then we have contents. Now this is a string where we're going to store the contents of the file. Then we have FD, which is actually the file descriptor. So let's do something like this. First thing we want to do, the name of the file is special.txt. So we want to do FD is equals to what? Open special.txt. Then we'll open it in 0 o read only. Yes, o read only. That means we just want to read it. We don't want to do anything. So we got to the file descriptor. Now we can do something like this. Start buff. We can just do start. Let's quickly check it. So we want to check the start of a file. We do man to start, right? So we have start, we pass the part name, or let's use f start since we have the file descriptor and pass the start buff to it. So something like this, f start. F start, mind you, yeah, we don't need f start, then we pass fd, which is the file's descriptor, right? Then we pass the address of the start buff. Now it has put that stuff inside it. Now size is equals to start buff, right? Dot st size, right? That's the size of the file. Now we can now allocate space for the content. So content is equals to my malloc, right? Now size plus 1. That one we are adding is for the null byte, right? Now we can do read. We are trying to read the contents of the file. So read, let's quickly check it out. So we have man to read. So this is going to be last thing. So just take note. We're trying to read the contents of the file. We have to pass the file descriptor. We have to pass somewhere to read it into, and we have to pass the number of characters we want to read. So we already have this. So first thing, file descriptor, which is fd. We're trying to read it. Then the stuff we're trying to read it into, which is content, right? Then also we pass the size that we're trying to read. So we're trying to read size. Then at the end of the day, we'll do content size equals to null byte. So we are adding the null byte at the end so that it's a official string. Now we come to the defining moment. So print f, right? Print f s. We have a new line at the end. Then the contents of the file, which is content. So you can see actually reading a file is very simple. So let's try that and actually see what's get printed out. I'll clear my screen and I'm going to run it. I'll do gcc my malloc file.c. I called it file.c. I mean, hopefully we don't get any errors, but we did. Typo error. So it's coming from supposed to be cs, right? So let's run it again. No errors. I'll clear my screen now as I'm going to run it, and you actually see the contents of the file printed out. Who's ready for this? Who is actually ready for this? Let's see if it works.
Go ahead, we are
Let's test
ready.
it out. I'm going to press enter now, and I actually pressed it, and I'll actually reduce the size of my terminal so that you see this. Okay, let me switch terminal. I'll switch to this. And we actually see what's get printed out. Who knows this?
Yay!
Yeah, yes. And this is how we come to the end of today's show. Yeah. And the show has ended. So I stop sharing now. I pass it on to
Dave. This was really cool. Wow. So
Surprise, surprise.
yeah, I was not expecting this. That's really funny. Guys, I will
Surprise,
tell you
surprise,
that,
surprise.
guys, you did an amazing job. I think, like explaining very simply in very simple terms what you're going to build, building the flow charts and then the code. And then like the code handling was like also very smooth. You're looking at the error message, looking at the, at the manual to make sure that you have the right prototype, you use the right functions, the syscalls and everything. I know like you guys worked a ton on these projects, but it shows. And I'm sure you've learned a ton of things. I know that we have like additional questions. So let me take on them, or maybe you can answer them, because you are the rock stars today. Question: so when we make another call, is it going to call an additional more space to the 10,000 or inside the 10,000 that you have allocated before? Who wants to answer that?
I'll take that one, Mr. Julian.
Go.
Okay. Okay. What happens is, until whatever we have in store, or until whatever we are having is used up, that is when another system call is made. You can't make a system call, or the machine can't make a system call if it has memory. It will, if whatever you've used, and then there is a balance when someone else calls, like when someone else requests for memory, it will use that until whatever it is having is used up. That is when they'll make another system call. Hope I'm making clear, like I'm making sense. I don't know.
No, it makes sense. Thanks, Daniel. Okay, next question. Is there any difference between C taught in class and this one? Who wants to answer? Josh, you want to answer? Josh is thinking, do I want to answer? He's not sure.
I can take it, Mr. Julian.
No, someone else. Alice, you want to take this one? Is there any difference between the C that we just saw and the C that is taught in class? I mean, taught at ALX, because we don't really have a class. Alice?
No difference. I don't think there's any difference. The only thing that we've done differently is rewriting our Malloc. But for the class sessions, we're going to be the class projects, or rather the ALX projects. We just focus on using can we call it the global Malloc? Yeah.
Yeah, Alice, this is actually one of the only function that is allowed from the standard library, right? Are we allowed to use printf or other like really cool functions like this? Alice?
Sorry, I didn't get the question. That was for me.
No, I was saying that Malloc is one of the only function that we are able to, that students are allowed to use during the program while going through C from the standard library, right? So I was just saying also that can we use? I was asking like, can we use like printf, for instance?
Yeah.
No, we can't.
What did you ask?
Can we use printf?
Malloc is from the standard library, yeah? You asked it to use printf.
Yeah.
During the project.
Can we use any other function from the standard library?
I know. Sorry. No, didn't get that. We can't.
No, we can't, right? Can we use F-scan? Scan F. Okay, the answer is no. Okay, last question. What is the best practice to allocate
No,
memory
yes.
when taking input from users? Who wants to answer this one? What is the best practice to allocate memory when taking input from users? Anyone? Brenda, you want to try? Tech giants, come on. Anyone wants to answer this?
I can give it a try, Mr. Julian.
Let's go.
Okay, one thing we have to put in consideration whenever we are asking for memory or whenever we are calling malloc is normally size of a byte, of a float, of an integer varies from machine to machine. So we are recommended to use size of, or we call, I don't know the best word I'm trying to get it. We try to use size of, like when we're calling malloc, we use size of, because the size of an integer, a character, a float depends or varies from machine to machine. We have 64-bit machines and then the 32-bit. So I guess I'm making sense. I don't know. Thank you.
It does make sense, yeah. I think the other thing that you want to think of is what is going to be the size of the user inputs. If you know that is going to be huge, you're probably going to create your program in a different way that if you think that most of the time is going to be small chunks in order to optimize your program. And the last thing is, as soon as you have allocate memory and as soon as you don't need it anymore, you want to free it. So in those examples today, we did not link malloc to free. Maybe another time. Right now, we just allocate and we can't free space with the versions that we showed you today. But with the real malloc comes like another function called free. And I'm saying this for C12, like everybody else knows this already, that allows you to free the memory space that you don't need to use anymore. So if you take a lot of data from the user or from like somewhere else, you're going to need to free some space at one point because otherwise you're going to run out of memory and then your program is not going to be able to continue working. Okay, is there any other question before we go? Yeah, so another one. So how was Dave able to allocate memory with calling sbrk function? Dave, you want to answer that?
Okay, so I would let me attempt it. So can I be heard?
Yes.
Okay, so basically just think of it like this. So the SBRK would probably stand for shift break, like shift program break. So it just shifts the program break upward. Now, shifting the program break upward is the only thing that SBRK does. Now, the memory allocation is an effect of shifting the program break upward. Do you get it? So just that's the after effect. Once you shift the program break upward, it happens that there's just additional memory. Do you get? So that's really the only thing that happens. Thank you.
Okay, guys, I think this is the end of the questions. There's other questions about the text editor, but I don't want to get into a war between Emacs and VI because I know I'm going to lose because everybody is using VI and I'm the only one to use Emacs because I'm a dinosaur and the old guy in the room. Guys, I want to say thank you. This was a very cool presentation. I hope everybody understood the work that came for this session. And I think you guys made you did a great job. It was very well explained, very well coded. I'm sorry for the viewers about the network, but this is live. This is live. So now you understand like how everybody what everybody goes through in order to finish the program. It's like It's unfortunate, but this is life, and this is not preventing us from moving forward and continuing and being successful. Thanks again, and we'll see you very, very soon.